D4 weight versus mass. It's important to talk about this distinction some more. So the weight is the force on a body due to gravity. I mean, that's the typical definition. You stand on a scale on the earth, you weigh yourself. So F equals ma, an application is that the force, when it's the weight, is mg. So the mass is m. And that mass, see, doesn't depend on the gravity at all. So that's the amount of stuff that you are. And if you go to the moon, you still have the same mass, but G is going to be different for different celestial bodies. So let's look at the weight on the moon. That's going to be your mass. Now you're going to have a spacesuit on, but let's use a suitcase or something where you don't have a spacesuit, so we can just like a block. You take the block and put the block on the moon. Then the gravity, acceleration due to gravity on the moon, see, this is going to be 1.625 meters per second squared instead of the 9.8. So on the Earth, the weight is mg Earth, where this is the 9 point, and you know, you could use the standard value. If you round it off to 4 significant figures, the accepted value is to do that. And then if you were to compare the weight on the moon to the weight on the Earth, it's very, very neat here that the masses cancel, because you have mg for the moon, and then you have mg for the Earth, and you're just getting the ratio of the g's, which should be the 1.625 over the 9.807. The meters per second squared, you know, going to cancel out. And this is surprisingly very, very close to 0.166. So I'm going to put down 1.6. It's not exactly 1.6, but that's 1.6 to 3 significant figures, because 1.6 is 0.1666666, you know, forever. So that means if you weigh 180 pounds, say on Earth, then on the moon, you're going to weigh 30 pounds. Ignoring the spacesuit. You'll have a spacesuit on so you don't die. All right, so that 1.6 rule applies to everything. Isn't that cool? So what I did here is I made a little study, and the data I got from NASA only used 2 significant figures, so you might find some deviation here, but you know, 2 significant figures, the 9.8 is going to vary in places on the Earth and stuff, so I think two significant figures is fine. So for Mercury, yeah, 3.7, 8.9, these are the meters per second squared, but I prefer to just look at the ratio. So 0.38, that's your weight on Mercury, 0.38 or whatever it is on Earth. 0.91 for Venus, 1 for Earth, whatever it is on Earth, it's going to be what it is on Earth, and then 0.38. Notice that Mercury and Mars are the same. Later, I'm going to show you a formula where you can calculate G, you know, for a uniform body. It's going to be based on the planet's overall mass and the radius of the planet.